So, hello everybody. Now let us go to the next lecture in this particular week. And today we are going to continue our discussion on stimuli guided processes. And we are going to discuss today about supramolecular aspects related to applications of photochemistry in the design of new molecular entities or supramolecular entities which can possibly function as, for example, artificial molecular machines. So let me write down. So stimuli guided processes. We are continuing that further, and today we are going to look at some fundamental aspects of supramolecular photochemistry, which can be extended to the understanding of artificial molecular machines. And here we would like to look at a definition of a supramolecular device to start with. So we have here a supramolecular device where uh, there are different components. There are different components present in this arrangement of functional groups forming a molecule. There are different components which are present in this arrangement of specific functional groups which are forming a molecule, such that each particular component has got a particular function. So a supramolecular device, now it contains these different components which are made up of different functional groups which make up this molecule, and this is essentially a very large molecule. And the individual molecular components have specific properties such that these properties are intrinsic to the system, that are intrinsic to the system. Okay. And also it is to be kept in mind that this entire complex system, which contains different molecular components made up of different functional groups, are essentially stabilized by a network of intramolecular hydrogen bonds. So there exists non-covalent interactions between the different molecular components or the functional groups that stabilize the arrangement of the molecules in this complex system. So the system is fairly complex. It's a large molecule. It contains different functional groups, and each component has got a specific function. And overall, there exist intramolecular hydrogen bonds or pi stacking interactions, different kind of non-covalent interactions which stabilize these components in that particular complex system. And obviously, these non-covalent interactions are weak, so we should be able to actually control these intermolecular interactions depending upon different kind of movement of molecular components within this particular complex system. So as I told you, the idea is to look at the application of a certain stimuli and then use it in the applications of artificial molecular machines. And in this regard, it has to be kept in mind that when you talk about a machine is an entity which takes in a certain input of energy and then gives out work. This work can be in the form of chemical work, electrical work, or mechanical work. So, what is a machine? A machine performs work. It can be chemical, electrical, or mechanical work, and the efficiency is very important for a machine. It is the work output by work input into 100%. And in the performance of the machine, we have to keep in mind that the waste processes have to be minimized, like heating or generating chemical byproducts, which have to be removed continuously. So heating and generation of chemical products or byproducts during the process of these operation of machines can actually reduce the efficiency of the machine. So instead of employing chemical energy, it will be nice if we can employ photons, that is photochemical processes, or we can employ electrons, that is electrochemical processes, to perform work. Okay, and so keeping in mind that we are going to combine the concept of machines and apply it to that of a supramolecular device, where essentially every component of this complex system plays a very, very important role. However, if on the application of an external stimuli, if on the application of an external stimuli, the functionality of the complex system is identified with the entire molecule itself. Now, this is important. Now, initially we were saying that to function as a supramolecular device, we give some stimuli, and there are specific regions of the complex system, specific functional groups or specific molecular components which actually respond to it. But instead of that, if the entire molecule responds to that stimuli, that means the functionality of the complex system is governed by the entire molecule, then this refers to the function of a large molecule only. So we have to differentiate between processes which involve large molecule and processes which involve supramolecular arrangement of molecules. And so if there is a stimuli and the entire functionality depends upon the entire molecule itself, that means you are not able to essentially deconvolute the contribution of the individual components. Now then this is the case of a large molecule which is being activated compared to a supramolecular device where the specific components only are being activated. So let us take up some this by a cartoon representation. For example, we have got different components which are identified as follows. So in this case, we can have this is a molecule which contains two components, a component 1 and component 2, and overall this is a complex molecule, and this arrow represents a bridging ligand, a covalent spacer, or non-covalent spacer as well. So these are the possibilities, and now we can have photochemical activation, and this can give rise to these processes. Or this process. So now you see it is either this particular component 1 which is being photochemically activated, or 2, but in this case it is the entire molecule which is being activated. So this is a reference to the large molecule, and this is a supramolecule. So this is how we distinguish between the two entities. We can take another example where we have got, so the star here indicates an electronically excited state. We can have another case where we actually put an electron into the system. It can lead to this, or we can have this covalent association or the backbone, or this. We can also remove an electron. It can form this kind of species. And we can also have, on the application of light, we can have a charge transfer process where electron can be transferred from one side to the other, or we can have these processes. And so this is called a charge transfer state, and this is also a charge separated excited state, which we also called as the primary separation. So now you have an electronic transition from, say, a donor part of the component to the acceptor part of the component within the same molecule. That is, we call this a charge transfer process, which happens in the presence of light. It can either be from if this is the donor to this as the acceptor, or if this is the donor to this as the acceptor, and this is the primary separation, which we call as the charge separated excited state. And it is important to keep in mind that now when you generate the charge transfer excited state, different processes can take place, and these kind of entities which are actually affected by light are referred to as chromophores. So chromophores are the important functional units or the structural building blocks which must be present, which are sensitive to light. And these photochemically active components now can undergo different photochemical processes. Okay, they can now undergo different photochemical processes. For example, let us start with the basic concepts. So we now have S0, which is the ground electronic state, the S1, which is a excited singlet state. So we now have the electrons. So this is the ground state, this is the excited state, and this is the energy which is increasing. So we first have a particular frequency, say h nu 1. So we have the electron which goes to the excited state, and then de-excitation to the ground state results in the process of fluorescence, where now we have the frequency of the emitted light which is less than that the frequency of the incident light. So we refer to this process as fluorescence, which can take place. But then we can have the process of intersystem crossing, where we now go to the triplet state, and the triplet state is characterized by both the electrons being unpaired, and so this is the excited triplet state. And from this state you can actually have the back intersystem crossing, or you can have the phenomenon of phosphorescence. That is, this is now referred to as, say I refer this to as h nu 5. Now following the process of fluorescence, the electron which has now been excited to S1, two different processes can take place. We can now have an electron transfer to another acceptor molecule. So we can have this, and now there is a low-lying acceptor molecule. There is a low-lying acceptor molecule, and we can, so the electron is now transferred, and from here we can have the emission back to the ground state. This I represent by S nu 3. So this represents the fluorescence coming from the acceptor molecule. So there is now a transfer of the electron to a low-lying acceptor, and that now emits the photon. It comes back to the ground state with frequency nu 3, and that is responsible for the fluorescence of the acceptor in comparison to the fluorescence of the initial species from where the excitation happened. We can also have excitation transfer. That means before the electron de-excites to the ground state, that energy is transferred to another acceptor, which can now emit light and come back to the ground state, and this results in the fluorescence h nu 4 of the external acceptor. Okay, so all these photochemical processes can take place. We can have first the fluorescence, then electron transfer, followed by fluorescence happening at a lower frequency from the low-lying acceptor. We can also have the excitation transfer, which we also call as the energy transfer process, which results in now promotion of the electrons from the ground state of the acceptor to the excited state, followed by de-excitation or by emission of luminescence, which corresponds to fluorescence happening from the external acceptor, and all these take place at different frequencies. So all these photochemical processes are very, very important when it comes to trying to understand the supramolecular photochemistry of fairly complex systems. So keeping these things in mind, it is now of relevance to look at some specific examples. Where we can apply the concept of supramolecular photochemistry to understand the behavior of artificial molecular machines. Now, in this regard, let us look at the first example, where we now have a system which functions as a plug socket model. So here we have got the bi-naphtho crown ether, So this is having the crown ether moiety, and we have the binaptho unit. This is the anthracinyl benzyl benzyl ammonium species. Now what happens is that when you add an acid, trifluorosulfonic acid here, then this particular nitrogen gets protonated and it forms a new species where essentially there occurs threading, where the anthracinyl moiety now forms a new chemical entity. And you can see here that this new chemical entity has got hydrogen bonds which are stabilized, has got the hydrogen bonds which stabilize this particular 1:1 complex. Okay, and in this particular state, if you now shine light, there then there will be a transfer of energy. This energy is now taken up by this binaptho unit, and then there is a transfer of energy from the binaptho unit to the anthracinyl unit, followed by emission of light, which happens at a different frequency, nu prime, which is less than that of nu. So this tells you that during the process of complexation, there occurs quenching of the fluorescence of the dibenzo unit, and the fluorescence which you observe is now at a lower frequency coming from the anthracinyl moiety. And now when you actually add a base, tributyl tertiamine, then this proton will be scavenged, and then de-threading will take place, and then it will again come back to the initial state. That means there will be no further connection between the plug and the socket. So this in and out state is very, very interesting, and this tells you about the fact that we can monitor the movement of the machinery. That means the anthracinyl moiety into the socket via the acid-base mechanism. So this reversibility can be established by monitoring this de-threading mechanism via a photo-induced energy transfer, where we have got the quenching of the binapthyl fluorescence and the sensitization of the fluorescence of the anthracinyl unit, which is linked to the ammonium ion. So this change in the fluorescence profile, because of this threading mechanism, actually controls the threading, and then the de-threading is controlled by the base, and the threading is controlled by the acid. So this kind of acid-based stimuli controls this movement of the species. Now we can take another example, another very interesting example, where we have got this Dapco moiety. Where we have got this particular unit, where you see the starting configuration is where there is strong hydrogen bonds between this dibenzo 18 crown 6, and then we have got the corresponding 4,4 prime bipyridine unit. This is the 4,4 prime bipyridinium unit. Okay, and this we have put these bulky stoppers here, and these bulky stoppers which are present here, they prevent the movement of this dibenzo 18 crown 6 out of this particular region. So this is like a stopper which we put here. Okay, now when you add a base, the addition of a base deprotonates this hydrogen, and once it deprotonates, then you destroy the charge assisted hydrogen bonds. When you destroy the charge assisted hydrogen bonds, then there is a movement of this macrocycle from this particular station, say S1, to this particular station, say S2. Okay, why? Because now this particular configuration stabilizes the crown ether, by charge transfer interactions. Okay, so now you see it comes here, and at this stage, if you now add the acid, so if you will again protonate this NH, then what will happen is that this is now a protonated species, and you can again have this species which is formed here. Now, if you want to reset this process, you will have to destabilize this particular entity. Now, destabilization of this entity can be achieved by electrochemical reduction of this bipyridinium unit, or you can do the oxidation of the crown ether moiety. So if you do the reduction, then this positive charge will go away. There will be this will now become a free radical. There will be an electron here, and that will destabilize the charge transfer interactions, and this will again go back to the initial configuration. Or if you oxidize this crown ether, this will have a positive charge, and there will be repulsions between these two entities, and this will again go back to the initial configuration. So you can always set these entities depending upon the different species which are present, and you can control these processes. So you started with a base, and then you had a movement of this particular crown ether, and now you can again bring it back to the initial state by electrochemical reduction or by oxidation of the crown ether moiety. And in the last example, we can see a much more complicated case where we now have a this kind of an arrangement where we have got different cationic species. So we have the starting arrangement where the crown ether is more stabilized by the pyridinium unit. This is slightly less positive because of the methyl groups. We have this electron rich system, we have the photosensitizer, and we have the stopper here. So the starting configuration is shown here between two stations A1 and A2. First is the transfer of the electron from the photosynthesizer to this particular A1 station. So you can see that this creates the radical cation, and now this is a unstable species, a relatively less stable species. So this can lead to now a process which we call as a ring displacement. So this leads to ring displacement. Okay, because now it is going to be more stabilized in this particular region, and the photosensitizer which transfers the electron becomes P plus. There are two competing processes. One is the ring displacement and the deactivation of the excited state by the transfer of electron back to the initial position. Now at this particular state, again you can have a electronic reset. You can have an electronic reset where the electron can now go back from A1 minus back to the photosensitizer. If this happens, then again this will be a less stable arrangement. This will be followed by a nuclear reset where it now comes back to the initial configuration. So you see that there are different processes which are involved here. So you start first with photochemical activation, photosensitizer, transfer of electron, reduction at the A1 station, then you have a molecular movement, okay, because this stabilizes the charge transfer interactions now, and then there is a back transfer of the electron to the photosynthesizer, that is the electronic reset, and then we have a nuclear reset, and we can control this process of movement, this intramolecular mechanism between the two stations A1 and A2 by controlling the processes involving this molecular movement with the de-excitation pathway. So these examples tell us that whenever you have a stimuli, say in the form of light, followed by movement of electrons, and these molecular movements can control the conversion of light energy to mechanical energy. So in all these processes, we have conversion of light to mechanical energy. So with this, we would like to complete this lecture. I hope you have been able to appreciate stimuli guided processes, and in the next week we will now go on to the other topics of discussion as well. Thank you.